is from Joya, and she's asking, what's your take on the role of chromospheres in red supergiants mass loss? Maybe Holly, you would like to address that question?
Yeah, it was a question to Ali. As I have seen Ali great talk, I really enjoyed it, and yeah, I've seen that you haven't mentioned it, but also to the community in general, you know, not only to Holly.
Holly, you mute.
Yeah. Oh, yeah, I would give this one to the community because I don't have that much experience in studying the chromospheres themselves of red supergiants. My background's more in the more extended circumstellar environment, so I would definitely open that up to the rest of the community to answer.
All right, feel free everyone to comment on that thread. So next question is from Marcelo Bertolami, who asks about red giant branch stars. So it's a question for the entire community, not only to the speakers. What is the current understanding about the physical mechanisms driving mass loss on stars during the first red giant branch? Not AGB, but the low mass RGB stars. Also, from an observational perspective, what have we learned recently? Would you like to comment on that? Holly, Sophia?
I don't think we have an understanding. That's my comment. I think, I mean, there are measurements of mass loss on the RGB. It's not that dramatic, but in some, I think I've seen some results where it's certainly higher than what we thought that it was, but I don't think we understand the mechanisms behind it. But I'm not a theoretician, and maybe there is someone who knows.
I know Martin Grondwegen tried to detect CO lines from red giants, RGB stars, and there were, I think, only two sources that showed some emission and very tentative wind signature. So we do not know much, even observationally. Maybe there are some optical observations of absorption lines, but that's it, not much more than that. Holly, you would like to comment on this point?
Yeah, so I also focus on red supergiants in my day-to-day research rather than on the red giant branch. So again, this is definitely something I'm looking to the community to learn more about.
Also, feel free to raise your hand on Zoom if you would like to comment on any of the questions that we touch here. And I think there is one raised hand. Jaco, you would like to say something now?
Yeah, I use my power, but anyone can raise their hands. Yeah, I see Umbra also. Just to comment on the RGB mass loss, and Andrea, I don't know if she's online today, but she and others have worked on RGB mass loss, and for a long period along the RGB, it's chromospherically driven. Only at the very tip, some RGB stars can develop strong enough pulsations and form dust shells. And there, from spectroscopic observations, it seems that becomes at least equally important as chromospheres. So the signature of chromospheres is starting to be a little bit washed out. But for most of the RGB, it's chromospheric. But Holly made a good point about the progenitors, because RGB stars become AGB stars. And of course, red supergiants have had a history before as well, whether or not that had a companion involvement that we don't no longer see. That happens at all masses. Yeah, it's not a feature just for massive stars, even though there perhaps the binary fraction of close binaries is higher.
Can we unmute Ambra, please? I don't think I'm able to. Oh, Ambra, can you unmute yourself and please?
Yes, I think I'm unmuted, but I cannot put the video on, but whatever.
Yeah.
I would like just to comment about what has been said.
Are you breaking up, Ambra? I think we lost Ambra. Maybe we can get back to her when once.
Can you hear me? Sorry.
Oh, now we can hear you. You're back.
Yeah, because I don't know, the connection was out for a while. So maybe better if I don't put the video on because maybe it's unstable. So yeah, just to comment on the gas to dust ratio, it is absolutely not true that we assume total condensation both in 2013 and 2014, as well as later works. We always follow grain growth coupled with the stationary wind approximation. And regarding the gas to dust ratio, we fitted, for example, the carbon stars in the LMC, and we find that the gas to dust ratio were in broad agreement with the hydrodynamical model. So no, it's not. We don't assume full condensation, absolutely not, and we don't assume that the gas to dust ratio is always 200.
No, I know this, Ambra. So I refer to your work in the sense that you give an explanation as to where this number 200 comes from, and I did show your work from later on where you have calculated it. So as an example of that, it's off, that it's not 200. So okay, I'm aware of this, but I'm sorry if that was unclear.
No worries. It's just to be clear, because like in the first time that was mentioned seems to be like in contradiction with the second time. So just to point out that yes, it was always okay. Thank you.
Yeah, thank you for that, Emma. Thank you for clarifying.
All right. So the next topic on the Slack channel, I would say, is an issue raised by Graham Harper about magnetic waves. Graham, would you like to summarize the thread you started on Slack? Would you please raise your hand so we can easily find you to unmute you? Oh, yes. Thank you.
I think you should better hear me now.
Yes, we can hear you.
Yeah, so the thread was, someone was asking about the mechanism that drives winds from the K, the single red giants and the Ks and the early Ms. And the consensus is that it's Alfvén waves, as pointed out by previous speakers. And the main reason for that is that these stars, they don't show dust, they don't show molecules, and acoustic wave models, shock models by Kuntz and collaborators, the energy of the waves just damps very close to the star and it can't drive a mass flow. So by default, unfortunately, Alfvén waves has become the consensus, but we don't have a really working model of how they work. And the main problem there is that to drive the flow and keep the terminal speed low enough, you have to damp the Alfvén waves, and that overheats the wind. That's what we do not observe. And that is one of the great challenges right now. So yeah, so Alfvén waves are plausible, of course, because we have measurements of magnetic fields. If you look at chromospheric lines, you see highly turbulent flows, very supersonic, presumably driven by Alfvén waves and turbulence. So we have all the ingredients. It might be the point that simple, steady 1D models are just not sufficient. And some models by Epeshin have tried to do nonlinear models, time-dependent ones. And those models are quite successful, but they don't have a very complete energy equation. So they're not able to address the heating of the wind. And so we don't have a check on that. And I did some work with Suzuki many years ago, where his time-dependent models, and his models, they produced a good mass loss rate, good terminal velocities, but the winds were 100 times too bright in the radio. So they just didn't work. So it's the energy equation, and in case we need the theoreticians and the modelers to maybe revisit these stars, because we know now their angular diameters, we know their masses fairly well. We know the distances, know effective temperature. So we know the stellar parameters really well, which we didn't in the 80s, pre-Hipparchus. So we know the stellar parameters, we have great observations from Hubble and the radio. So we just need more Alfvén wave models which have an energy equation that can allow us to test them, for example, in the radio. So that's that was the thread that I was responding to.
Thank you, Graham. Susanne, would you like to comment on this or other issue?
Yeah, no, I actually really want to comment on this particular issue. It was going through my head, as far as I understand, the argument for RGB mass loss comes basically from saying that the mass must be lost before the AGB, because otherwise population synthesis studies and so on don't fit. So it's kind of a theoretical argument, and it seems to be very hard to actually measure the wind properties. So is that picture basically correct? Because otherwise, I think I have roughly the same picture as Graham has. So yes, there are Alvean models, but Alvean wave-driven models, but they don't work very well, or they're not very realistic, so to speak.
Thank you, Susanna. It seems that we neglected red giant branch stars for too long. Yes, please continue.
I think the point is that the mass loss rates are much lower, so it's harder to measure the stuff. But of course, you have much longer time on the RGB. So even if you have much lower mass loss rates, then you will get an effect from lower mass loss rates. But it's harder to do, I think, both theoretically and observationally. All
right, thanks. Joya, I see your hand has been raised for quite a while. Do you want to say something?
Yes, so I want to continue on this point and also the previous point by Graham. So yes, so in red giant branch stars, we see that the mass loss is powered by these alpha waves. And observationally, we can see this chromospheric diagnostic lines, the one that I wrote. So here, magnesium 2, iron 2, aluminum 2, and mostly in the UV. I just wanted to, and I mean, it's clear that this activity is stronger for stars that are less evolved and less pulsating. I just wanted to ask the community and ask what are your thoughts on the necessity to investigate how this activity evolves with the increasing of the evolution with the evolution of the stars. So when the stars evolve, and if this is a need that we need to investigate, or what are your thoughts? Because it has been said that later on the AGB is clear that these dust are dust driven. So where is the point where the star becomes dust driven and the magneto-hydrodynamic alpha waves don't just work anymore? Thanks.
Yeah, so the question must be very hard. No one wants to answer it, at least no one present with a microphone. But Jaco is very impatient to ask another question.
No, to just a very briefly comment. That's also from what Susanna basically asked. Is there direct evidence for mass loss? Yes, there is. But also there's a very strong constraint from astroseismology, comparing, for instance, red clump stars and RGB stars in the same cluster. And that's very helpful, and it's something also Holly pointed out. It's the endpoints and the starting points which tell you the constraints, and those are the boundary conditions with which you lose mass. Also to say something nice about Sophia's talk, which was also great. Indeed, if you ignore the fact that the gas to dust ratio could be much higher, then you might underestimate the total mass loss. So where we didn't and directly derived it, we do get very high mass loss rates, and I think we will have reached the maximum that's kind of possible within those boundaries that I just described. So if you're suggesting, but maybe I got it wrong, that if you have a more slowly accelerating wind, that becomes even worse, then I think we might get a sort of a mass budget problem.
All right. I suggest we go back to the Slack channel and move on. There is actually next thread is yours, Jaco, about the Goldman and Marshall papers. Would you like to continue on that point?
Well, that actually is what we did. So directly derive the gas to dust ratio from the wind speed, which we measure directly, and feeding that into the SED modeling. So that's essentially what Sophia is advocating. We do, which of course we cannot do for all stars, because we cannot always measure directly the wind speed. But as he points out, there are other uncertainties as well. Also like Steve Goldman, who just put a comment in the Slack, points out other assumptions such as spherical symmetry. I don't want to open a Pandora box, but.
Mm-hmm. All right. So the next thread is opened by Chrysler Sandin. Sorry for butchering your name. Regarding the gas to dust ratio, it depends on the dust velocity emphasized, which isn't really observed. Dust / drift velocity values obtained from observations using a stationary model result in too low values. It seems, see my 5-minute pre-recorded talk. And there is only one model that calculates dust velocities. And another follow-up comment on this is a suggestion that to account for gas to dust drift, there is a factor of up to 5 missing owing to this aspect only. Sophia, would you like to comment on those remarks?
Yeah, I'm not sure what the factor of 5 really refers to, but yes, of course, the dust velocity is the velocity that you need to put in order to get the density of the dust. So that is very true. Christer Sandin is how you pronounce his name.
Okay. The next comment on Slack is by Ambra, but I think we already addressed it with Ambra commenting with her audio. And the next big topic is by Phil Massey. Phil, would you like to ask or make your point with the microphone? Yes. Can we please unmute Phil?
This session.
Yes, we can hear.
15 minutes.
Hi, I just was curious about the whole issue of what the current thinking is about what drives the mass loss in red supergiants. I was a little surprised to hear that the assumption is that it's dust. I thought this was a very controversial and uncertain thing. There is very excellent discussion, though, about this now on the Slack channel.
Okay, so please comment on that thread on the Slack channel. The next question I see is actually by Stefan Utenthaler. Sorry, Stefan. The question is to Sophia. With the new observational possibilities available today, would it make sense to redo your 2008 study with a larger sample, improved results, etc.? Sophia?
Yes, definitely. And we're trying to do this as well. But it takes a little bit of time. So we are working on this project where we have 200 nearby AGB stars, and we're doing both the dust modeling and the gas modeling. But until now, we don't have clear results to show because we're still in the process of deciding exactly how to do this in the very best way. And this is what has resulted in the presentation that I gave today, digging into this problem. But it will come if you're patient enough.
All right, sounds good. The next one is by Andrea Dupree. Andrea, would you like to ask your question with your mic? Do we have Andrea there? Well, I don't see her raising hand. So maybe I'm just going to read the question as it stands on the Slack. The helium-1 10830 line has revealed fast, that is 100 km/s winds in red giants. Mesharos et al. Modeled RGB mass loss in several globular clusters, found a metallicity dependence as well as variability in the mass loss rate. I guess this is a comment to our discussion about the red giant branch stars. So let's move on to the next question. There is a comment from Steve Goldman with a few replies. Do we have any hope calculating errors on mass loss rates for individual stars outside of our galaxy when we assume spherical symmetry? Sophia?
Yes, so I think actually we have the tools to do this now. I mean, so we have reasonable enough 3D radiative transfer models where we can do some kind of estimates of both clumpiness, which I just saw was in one of the comments coming later on this thread, and but also, I mean, let's say common structures, so structures that we see in the nearby stars, like what Taisa showed us yesterday. So if we're assuming if there's a spiral with a density variation of a factor of 2 or something like this, we can actually, using the 3D models now, estimate what kind of errors we will do by assuming that it's all smooth. But this is again something that takes time and it's not so easy to do. So but it's possible to do if you have the resources to do so. Mm-hmm. There was another question, no?
Yeah, about extragalactic sources, individual stars in extragalactic.
Yeah. So I think it's very possible to do that, calculate the errors, or at least estimate what kind of errors that we do when we assume that everything is smooth and spherical and wonderful.
So that was a question by Steve Goldman, but commented on it were also Ben Davies and Yorick Vink. Would any of you would like to ask a follow-up question or make a comment on this issue? Please raise your hand. 3, 2, 1. Okay, let's move on to the next question.
Yes? I can actually comment because I'm reading it, and he says that he doesn't think that it's that big of an issue to include this inner region. But I mean, of course, this depends on all the other assumptions that you make about your star. But I did test it for several different optical depths. So the one that I showed is not for any extremely thick star or anything like this, but it will make a difference also when you have a thinner circumstellar envelope. So I think it's a bigger issue, at least, than what we thought that it was, at least what I thought that it was before I looked into it.
Mm-hmm. Okay, I think the next point is going back to the discussion about RGB stars, and it's by Markus Witkowski. For red giants on the first giant branch, do we think that the wind is gas only, or are there indications that they also form dust? And Stefan replied to that question. There seems to be a limit of pulsation period of 60 days for which on the mass loss also becomes dusty. And he quotes some papers which address this issue. This can be stars close to the RGB tip. All right, I think we're going back to the to discussion that Graham initiated, and he replies to Susanne Höfner that she's correct. The low mass loss rates means that they are hard to detect. That is why the UV is crucial, because the line opacities are high, allowing the wind scattering to be seen. The next comment is by Ken Carpenter. Ken, would you like to ask the question or the comment with your audio on? Yes.
Okay, thank you. Yeah, just following up on Graham's note. Indeed, the lower mass loss rates are visible if you use UV line profiles. These are very strong chromospheric lines that show absorption reversals due to the overlying wind. So by modeling in detail the profile of the lines, you can measure the change in the wind velocity versus height and other wind parameters, and in the end derive an estimate of the mass loss rate. And this does confirm the low rates that I think people are expecting. There's a paper by Joya that summarizes the work that's been done in this area. over the years. And the 2M giants in the paper, Ugem and Gam crew, come in about 7 to 45 times 10 to the minus 11 solar masses per year. There's a couple of K-stars in the paper, and they're about 1 times 10 to the minus 11. So fairly small numbers. The same technique when applied to the red supergiant Lambda Val, a K supergiant, comes in about 2 orders of magnitude larger, so 10 to the minus 9 or so. So it is possible to measure the mass loss rates in these stars, but as Graham says, the UV is critical here because you finally have something with enough sensitivity, enough opacity to sample what's going on.
But is it measuring all the phases that are possible there, or are we just biased to the ionized part of it?
Well, we're measuring. You've obviously read the papers here. I think a lot of the measurement is done with ionized iron 2 lines, magnesium 2. But we do attempt to scale to total mass loss rate. Now, of course, there are assumptions and certainly imprecision involved in that. Nonetheless, I think you get a good handle on the magnitude of the mass loss rate here. I wouldn't quote to the nearest 10th in any of these numbers.
All right, thank you, Ken. The next question, I hope it's a question, is by Janet Bowie. What is the underlying assumption about the dust mass in the dust to gas ratio? I know this is background stuff that you all know, but it's probably a systematic problem. Sophia, would you like to address this question?
Yeah, so I looked at the thread, and I think Jaakko has answered it very well. So it's yeah, so so Jaakko's answer in the end is essentially that it depends on what you assume for your dust, and this was kind of the door that I didn't want to open, because that is a whole issue in itself, which type of dust you want to use, what you assume for that dust, and what type of measurements you have for the optical properties of that dust as well. And yeah, this is the next step, I guess, to figure out how big errors this will make.
And you don't want to talk about this because it's a problem with opacities, laboratory data?
I don't want to talk about it because I only had 15 minutes in my talk. I had it in the beginning when I started doing my talk, but I took it out because I realized that it would take me, I don't know, hours to just explain some of the problems.
Okay. The next question is by Tim Lawlor. Tim, would you like to ask your question online? Please raise your hand if you do. Yes, let's wait for Tim. Joya, can we unmute? Oh, yes, thank you. No, Tim disappeared.
I had just promoted him to panelist.
Yeah, me too.
Where is he gone?
Sure. Is there?
Tim, you need to
unmute. I got kicked out and then I came back in. So yeah, so the question's a little out of my wheelhouse, but I have colleagues who, when they talk about winds of from red supergiant stars, they're always talking about line-driven and radiation-driven winds. And I guess so. I guess I'm just curious why I'm not hearing more about those. They use a code called Zeus to model the winds of very massive stars. Is that something? Is it just that those people who use that are not here, or what role could that play in modeling winds? So like line-driven winds.
Anyone would like to take that question? Susanna is still on, I think. Maybe Ambra or Sophia. Anyone?
Well,
yeah.
I can answer for me saying that this is, I mean, this is not what we have in the stars that I studied. So I only studied the low mass ones. So
But me
I'm not the
too,
right
yeah.
person. Yeah, sorry.
Susanna, please unmute yourself.
Thanks. It's not directly what I'm doing either, but my impression is the line-driven stuff is for massive, not so much evolved stars, so for hotter stars. I'm not sure you can do line-driven winds for the cool massive ones for the red supergiants, but that's only a feeling. I haven't looked into it in detail.
Right. Okay. I think that sounds right.
All right, Jaco.
Yeah, just to follow up and to confirm what Susanna says. So some early type massive stars, they have line opacity for two reasons. Because they are hotter, so there are many more transitions becoming available, and secondly, because they are emitting most of the light in the UV, which is where those lines exist. And so of course that at some point disappears when you go towards the cool part of the Hertzsprung-Russell diagram.
Right.
And so radiation-driven winds in the cool end of the spectrum will generally be continuum-driven rather than line-driven.
Okay, and I think we have still 2 minutes to ask one more question. And I see Marcelo asked one on Slack. Marcelo, would you like to unmute yourself and ask it right away?
Okay, thanks. So it's rather simple question is whether I mean, in fact, it was somehow already addressed in the Slack, but do we expect RGB winds to be metallicity dependent given the proposed underlying mechanism that we have? I mean, if winds are driven by Alven waves, do we expect them to be metallicity dependent?
Holly? You mentioned metallicity.
Yeah, so like I said, I'm more of an expert on red supergiants rather than the RGB ones. So I wouldn't know so much also because I don't know so much about the wind launching mechanisms at the base of the wind. So it's definitely one to ask to the community of experts about.
All right, so the Slack channel is open. Everyone who's interested in this topic, please comment or ask questions at the thread started by Marcelo. And I think this concludes our session.
Sorry.
Yes. Yeah.
I'm sorry, Tomek. I saw that Yorick had the end up since a while, and I just.
Oh, okay. Oh, sure. Yes. Yeah, absolutely. Yorick, please.
Just because there was a discussion about the hot star winds, and so often people think hot stars have stronger line-driven winds than cooler stars. That's actually not the case. More massive stars are more luminous, and therefore they have stronger winds. But if a star has the same luminosity, in the first instance, the mass loss rate goes down because, as Jaco said, you don't have the hot UV anymore. But then you come to a 20,000 to a opacity bump, called the visibility jump, the mass rate goes up. And it happens again at about 10,000 Kelvin. When you get into the yellow hypergiant regime, you get again an increase in the mass loss. Now, then at some point towards cooler stars, you have no opacity anymore, no gas opacity. But we have, of course, dust opacity below 3,000 Kelvin. And for me, always the interesting question is, why do stars of 5,000 Kelvin, where there's no dust, where there's no line opacity, still have such high mass loss rates? And I think there's a lot of interesting physics to be learned in those stars. And maybe Holly wants to say something about that.
Yeah, I agree. I think that there's a lot we can learn about trying to understand what the launching mechanisms are, both by considering it from the point of view of coming along from, as you say, the hot massive stars, where we have these radiation line-driven winds, and then comparing to the low mass ones where we've got, again, so much cooler and so different as well. And I think it's also important to take account that you can get evolved stars that are still experiencing these radiatively line-driven winds, like Wolf-Rayet stars, for example, where they're still hot enough. And so it's important to know what all of the different stars are doing with their winds.
Okay, thank you both. I think now we already entered the break time, so I give back the mic to Joya and Jaco. I guess we have a break of 20 minutes?
Yes, so
28 minutes.
Yes, exactly. Thank you, all the speakers, and thank you, Dominik, for chairing such on time the session. And so, yes, we will resume at 2:10 p.m. UTC time. Thank you.
Go have a look at the virtual biscuits that Simon brought yesterday, I think.
Thank you all for excellent talks and questions and comments.